When I started to prepare for this talk and I was looking at my own abstract, I was a little intimidated. So I thought, like, I don't know what I was thinking when I wrote this abstract, that I was going to teach you for like 3 days or something. So what we'll do is I'll try to give you a flavor of state space modeling, and then you can decide whether it's worth to take a 2 or 3 or 4 day course afterwards. So the way that this is different from the previous 2 talks is that now we are going to focus exclusively on single subject analysis. So we are going to look really at time series models. State space modeling is a technique for time series data. So you have many repeated measures of a single subject. And then you might have it of multiple subjects, and then you can compare results across subjects. So first I will try to build a case for this single subject approach. And you probably have seen, if you've seen the presentations by Peter Molenaar, then you know this stuff, but I'll just present it for those of you who do not have this so clearly in mind yet. And I want to start with this really interesting paper by Bernard Schmitz, who also was at the first meeting, and Skinner. And they studied academic performance in children. What they did was, first they studied it cross-sectionally. And what they found was that children who experience more control put in more effort. Children who put in more effort perform better. And then children who perform better experience more control. Now, if you are a little bit like me, you are tempted then to think, oh, it's a cycle. Yeah. I don't know, like, does everyone feel that way? Yeah. But this is actually the question. We are looking at cross-sectional data. We are looking at differences between children at one occasion. So the question is, does this translate to a within-person process? So is it true that, idiographically, at the process level, is it true that if a child puts in more, if a child experiences more control, will it put in more effort? If it puts in more effort, will it perform better? And if it performs better, will it actually experience more control? And what they did in this study is, after the cross-sectional part, they also studied a small group of children over an extended period of time, and they looked at those relationships within these separate children. And they found that some of these children had a pattern that was very similar to the cross-sectional result, but there were also children who had a very different pattern, who, for instance, after performing well, would actually put in less effort the next time. Because, you know, if you did well, why would you put in that much effort? Or if they performed really badly, they would put in more effort the next time. It's a wonderful study that empirically shows that cross-sectional results cannot be translated to the within-person level. And the question then is, do we do this all the time? I think yes, but it's often not done in a very explicit way. So one example where it's done very explicitly is in personality psychology by McRae and John in this quote, who say personality processes by definition involve some change in thoughts, feelings, and action of an individual, and all these intra-individual or within-person changes seem to be mirrored by inter-individual differences in characteristic ways of thinking, feeling, and acting. So if you assume this is true, then you can study cross-sectional data and get some insight in the process. Other people don't agree. For instance, Epstein wrote, too often the highly questionable assumption is made that correlations derived from nomothetic studies, so that's cross-sectional studies, of groups of individuals are applicable to processes within individuals. And another one by Grice is establishing the validity of a nomothetic principle that holds for all people would require the study of individual persons, not simply aggregates of persons, what we do in cross-sectional research. So a true study of personality, or maybe of any kind of field in psychology, is therefore necessarily idiographic and nomothetic. So let's look at this issue in a bit more detail. What underlies this debate? Well, if we look at an example about the relationship between the number of words that a person can type per minute and the percentage of typos that they make. If we look at this cross-sectionally, we might find this negative relationship. So people who type more words actually make fewer mistakes than people who type people who type a lot of words make fewer mistakes than people who type very few words. Now here, nobody would translate this to the within-person level, saying, okay, now if only I type faster, I'm going to make fewer mistakes. Because you know at the within-person relationship, there will be a positive relationship. So for each individual, if they type faster, they are going to make more mistakes. The point here is that the cross-sectional relationship, it's actually a weighted sum of two different relationships. The within-person relationship, which we see over here in the red ellipses, and the between-person relationship, where between is really referring to between as in multi-level modeling. It's like stable differences between the individuals. So if we look at a particular individual here, this person, if we would do the same test again and again, they would have different scores on each test. But on average, this person's score on the x variable would be this, on the y variable it would be this. And we see that this between-person relationship is actually a negative one. Why is this the case? Probably because over here we have people who have a lot of experience or a lot of talent in typing. And over here we have people who've hardly done any typing, and so they type very slow and they make a lot of mistakes. So this is showing that the cross-sectional results, it's a weighted sum of within and between. And often this distinction between, so when you look in the literature on the nomothetic ideographic debate, they are making the distinction between cross-section and within. They are not really making the distinction between cross-sectional and between. Because I would argue if we look at cross-sectional data, when we want to study processes, we cannot do it. But also if we want to study traits, it's not the best approach because we have this state variance in there as well. So to give you an example of this, suppose cross-sectionally we find a negative correlation of -0.4. Then maybe at the within-person level we actually have this same relationship, or maybe an even stronger relationship. And then at the between-person relationship level, we have here the same relationship. So then it's the average of those two. It's just the cross-sectional result. Over here, it's also the average of the two. And so we get the same cross-sectional result, but we don't know what's underneath. So far, I've assumed that all individuals have this same within-person relationship. Of course, this is also not necessary. Maybe there are some people who actually type and make fewer mistakes when they type faster. So that is also something that we can keep in mind. This is by another paper by Bernard Schmitz, and he was also showing this, this cross-sectional correlation is actually a weighted sum of the within-person correlation and the between-person correlation. And it depends how much of the variability in your data is on one level or the other, whether the cross-sectional result mainly reflects the between-person or mainly reflects the within-person relationship. And when you think about this, it's actually quite disturbing, to me anyway, because when you think about all the kinds of analysis we do, like regression analysis, ANOVA, factor analysis, they are based on the correlation or the covariance structure. So we are basing all our analysis, or a lot of our analysis in psychology, on something that is an arbitrary mix of within and between that we cannot tell apart. We can only tell it apart under certain circumstances when we have repeated measures, or if we have data of only one person. Because if we have data of one person, there is no between-person variance. Then by definition, all the variance that we observe is within-person variance. This is also something that Cattell was pointing out. And he presented this idea of the data box. I don't think he called it Cattell's data box, but other people have started calling it this. indicating that you can sample from different dimensions. So you can sample from the dimension of variables, the dimension of persons, and the dimension of occasions. So cross-sectionally, you will sample multiple persons and typically also multiple variables. And then you just take a slice out of this box. If you think about standard longitudinal research, panel research, where you have maybe 4 or 5 measurements, you do the same thing, but then a couple of times. So you get a few snapshots of the process, and then you try to figure out what was going on. Another thing that you can do, which Cattell proposed, was just take one person, multiple variables, and a lot of occasions. And then you look at the actual dynamic structure within this individual. So you take a lot of snapshots, relatively close in time, and then the point is to look at it in the right way so you actually see the movie that's underneath. Yeah? So that's what we try to do when we do time series analysis. As Peter Molenaar and Bernard Schmitz were already pointing out in the first seminar, so we should be studying processes, and you should not aggregate. At least that's their opinion. And that's also, today, a little bit my opinion. Actually, I think there's 2 approaches when you do research, process research. So one would be a top-down approach where you use a multi-level model, where you allow, so everybody basically has the same process, but maybe there's quantitative differences. People have a different mean, they might have a different autoregressive parameter, so there's allowed, quantitative differences are allowed, but everybody has the same process. Another option is to use a bottom-up approach. So you really do separate analysis for each person. And then if you have multiple persons, then you can see whether the results replicate in other persons. And that's more the approach that Peter Molenaar and Bernard Schmitz were talking about. And will be the approach that I will be talking about today, although I do a lot of the other as well. So this brings me to the question, what is state space modeling? And because it's a technique we use for time series analysis, I start with what are features of time series analysis? Well, it's focusing on the temporal dependencies in the data. So we could say it's focusing on the autocorrelation in the data. So how do the subsequent measurements relate to each other? Now, characteristic of time series analysis is that we have one subject, or in econometrics, of course, it's not a subject, but it's like the currency of the dollar or something. We have a great many number of repeated measures. We say sometimes we need 50 or more repeated measures. So it's really different than your traditional longitudinal data where you have 4 or 5 repeated measures. And typical also is that the observations are ordered in time. So that's a very important aspect of time series data, which is very different than from cross-sectional data, where there is no order in your individuals. Here you have multiple observations, but they're ordered in time. The goals of time series analysis, when you look into the time series literature, it's really about predicting and forecasting. And when I say forecasting, I really mean predicting the next 2 or 3 occasions. And this is, of course, if you are in econometrics, you want to know, should I buy, should I sell? This is very important. You don't really need to know what's true in the long run. You just need to know what you have to do tomorrow. This is also true for the weather, for other applications of time series analysis in other fields. Another thing that they do with time series analysis is something called signal estimation or signal detection. That's what you use the Kalman filter for, which you might have seen in my abstract. And it's basically a way of estimating a latent variable. I will say some more about this in the next couple of slides. And another goal could be to identify the process, the nature of the process. So in the previous talks, the focus has been mainly on first-order autoregressive models, but there is a whole world of different time series models, and you might be interested in what gives the best description. I think from a psychological perspective, that would be a very interesting question. Econometricians care less about this. They just want to have the best forecast. So maybe you do not have the correct model, but if it leads to better forecasts, they are happy. So it's a very different way of looking at things, and that's why sometimes the time series literature is also very difficult to digest for someone coming from psychology. Apart from that, they try to write things with many equations as difficult as possible. State space model, it's a really flexible format that can be used to specify different time series models. So people call it the state space model. I prefer to call it the format because it's our framework, because it allows for so many different options that to call it a model is giving the impression that it's just one option. It's often combined with what is called the Kalman filter or the Kalman smoother, and this is Mr. Kalman receiving the National Medal of Science. So he's from Hungary, and so the Kalman filter and smoother, they can be used to either estimate the states, so it's the latent variable underlying the process. So you have your observations, but they are noisy. There is measurement error there, and you want to know the underlying process, like a latent variable. So that's one option. And then along the way, you can also use it to estimate the parameters of your model. And that's what we are typically doing when we are using the Kalman filter, because typically we don't know the parameters. So we have to estimate the parameters as well. The basic framework looks like this. And it's very similar to structural equation modeling for those of you who are familiar with the equations there. So there's a measurement equation which relates our observations y, and this could be univariate or multivariate, and it relates them to the latent variables or states A. So we see here, we have these different matrices or vectors in here. These are the constants or the intercepts. We have a matrix with regression coefficients or vector loadings. And then there is a residual part for which we estimate a covariance matrix. And then there is a second equation, the transition equation or the state equation, and it relates the states to the states at the previous occasion. This actually looks like an autoregressive model of the first order. That's actually what it is. It's just a vector autoregressive model of order 1. The thing is, however, that we can use this, together with this actually, to specify many different models. It doesn't have to be only a vector autoregressive model of order 1. Sometimes it's a bit of a puzzle how to get the model into this framework, but you can do almost anything with this. So here we see, and we have this matrix here would be with the autoregressive and the cross-legged parameters. We have a constant here also and a residual term for which we estimate a covariance matrix. If you want to know more about the relationship, there's a paper with Simin Chow in which we compare SEM and state space modeling to each other. Visually, with colors, it would look something like this. So we have a latent process here. That's why we use the circles. So these are all latent variables. And we relate the latent states, so two latent states at occasion t on the preceding latent states. So we use the green arrows here, which relate to the green matrix here, so the autoregressive and cross-legged parameters. And then we have a measurement part, so that's over here and over here, where we relate the observed variables, the squares, to the latent variables. So that's what we do with the measurement equation. And so Z here is related to these vector loadings. This is showing that the state space model can be thought of as a latent vector autoregressive model of order 1. But as I said before, you can do many other things with this same structure. So let's look at some things that you can do with this using an empirical example, which actually comes from clinical psychology, because that's where I have my original background in. And we are looking here at bipolar disorder. And in this disorder, people are characterized by severe changes in affect and activity, and they suffer from manic and depressed episodes. So this is the data of one of the individuals that we have. In the end, we will have 3 people with bipolar disorder and 11 people who are healthy, normal. So we look at positive effect and negative effect. And we were looking in the literature, and they have this theory that bipolar disorder is related to dysregulation of the behavioral approach system. I don't know how familiar you are with this, but it's if the BAS is active, you expect rewards, you have hope, difficulty inhibiting your behavior when you're approaching a goal. So if this would be extreme, it could be mania. And an inactive BAS is not expecting any reward, difficulty to be motivated, despair, so that would be depression. This is mainly related to positive affect, whereas negative affect is more closely related to the behavioral inhibition system, which is a fear-related system. When we looked in the literature, there were 2 kinds of descriptions of this dysregulation. One would be the roller coaster ride. It's just you are overshooting, and it takes you a much longer time to regulate back to your baseline. Then you're undershooting, and it takes much longer than in normal people. So that's one idea. And the other one was more like either it's switched on or it's switched off. So either it's activated or it's not activated. So this would be this regime switching system. So what we want to do is we want to look at different time series models that mimic this kind of behavior. So we have 2 models for the roller coaster and 2 models for the regime switching. We also have a benchmark model. This is just the white noise model. So here again we have the observations, but they're not related to each other over time. So every day is just a new day for this person. When you look at the autocorrelation function, that's also what you see. There's no relationship between the variables at different legs. Just random fluctuations. Then the first model that represents this slow return to baseline is actually the AR1 model, which we've seen already. So there is every observation is regressed on the preceding one. So there's some carryover effect from one day to the next. And depending on how this autoregressive parameter is, the carryover is more. So here we have a parameter of 0.3. So you see there's some carryover when you look at the autocorrelation function. Here we have an autoregressive parameter of 0.9. So you see there's a lot of carryover. It takes much longer to return back to the baseline. You see it also in the autocorrelation function. Second model is the Arima 011 model. So this is within the larger framework of Arima models. And it's been interpreted as a model that actually balances preservation and adaptation. So I think I will skip the actual interpretation of all of the explanation behind it, just pointing out that if this theta parameter, which we see here, is closer to 1, then there's more regulation back to the baseline. If it's further away from 1, actually it takes longer to get back to the baseline. 2 examples of those here. So here we have a theta of 0.55. So you see it takes much longer to return back to the baseline. Here we have a theta of 0.99. So then you are basically immediately back at the baseline. Then we have 2 regime switching models. So this one is just a hidden Markov model. So you switch between 2 regimes. And the regimes have different means and maybe also different variances. So, and the switching is determined by this, basically a first order Markov model. these are some examples of the kind of behavior that can be generated with this. And then we have another regime switching model, which actually combines the hidden Markov model with this autoregressive model. So you see there is some carryover also within the regimes, but also from one regime to the other. If you switch from one regime to the other, you also regress on the observation of the previous regime, so the switches are a little smoother than in the previous model. So our expectations would be that qualitatively, so are there really like different models for these different groups? We said, well, we do not expect the white noise model to be a good description for people with bipolar disorder, but apart from that, we don't have very clear expectations qualitatively. Quantitatively, we would expect that the AR parameter is closer to 0, so there's less carryover in controls than in bipolar disorder. For the Arima model, we would expect the parameter to be closer to 1 in controls, so there's, again, less carryover. And then with the regime switching models, we expected to have more clear differences between mania and depression in BD patients, but not so much in the healthy controls. This is the model probabilities that were based on the BIC. It shows that for each person, basically, there was a very clear winner among the 5 models because the probabilities is very close to 1 for one model and then close to 0 for all the other models. But we also see that we get different models here for the patients. So 2 for regime switching models, 1 that's more the roller coaster model. And then for the other, the controls, we also see that we select those 2 models or those 3 models sometimes. So we look at the quantitative differences between patients and controls in these cases. So for the roller coaster model that was selected for these individuals, so 1 patient and 3 controls, we see that this theta parameter that was crucial is indeed closer to 1 for the controls, indicating more preservation, whereas it's lower for the patients. And when we look at the results for the regime switching model, we found that the differences in means between the regimes was very large for a positive effect in the 2 patients, but the controls, the difference in the 2 regimes was not really in positive affect. It was only a negative affect. So they have a regime where they have higher negative affect or lower, but no changes in positive affect, whereas the patients have much more changes in positive affect, which makes sense because it's related to BAS, which is supposed to be dysregulated. So this brings me to the discussion. So state space modeling, which is actually developed also to fly space rockets into space. So the strength of this is really that you are focusing on the process. You are making no compromises. There's no aggregation across individuals in any sense because you're just analyzing the data from one subject. And I would say the sky is the limit. There's a lot of different time series models out there in the econometrics literature. And it's just the AR1 model is just one model, but there's a lot more. The disadvantages then are, well, okay, we have this n=1 approach, so how do we aggregate? If we just want to describe one person because we want to monitor this person and we want to predict when this person is maybe going to become manic, then this is a good approach. But if we want to gain more scientific knowledge, we want to say something more about how do these people differ from other people, and that can be really more problematic, although Peter Molenaar and people around him are working on different methods for doing this. And another thing is, well, so it's extremely flexible, but then, yeah, how do you choose your model? It's like we run a number of models here just because they seem substantively interesting, but I'm sure that other people can come up with a lot of other models that might also be a good description of the process. So that's really something. If the sky is the limit, then yeah, where do we go? So I think that is something that we will need to work on, and that also substantive researchers will have to have an important input in how do they think about these kind of processes. Which brings me to the end. Thank you.